If interested in learning about gravity, you've come to the right place. Welcome to episode 5 of the Boggling Universe series. As I mentioned in a previous episode, there are 4 forces that comprise our universe. I refer to them as the Gang of 4, and they are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Now, as you're going to come to find out, these forces are just vary so much from one another. And you'll come to realize the importance that they have in terms of the universe and our existence, because without them, I wouldn't be sitting here making this video, and you wouldn't be listening and watching this video for sure. So let me get into why I chose gravity first, and there's a good reason why I did. Not that it really matters in the whole scheme of things, but way back when the Big Bang occurred and the singularity basically spewed everything out into the newly formed universe, that one of the things that it released was the forces of the universe. It basically clumped them all together, and then individually, shortly thereafter, they started peeling off from one another, forming their own force. So gravity was first, and then the other 3 followed. The order really doesn't matter. So the theory that describes that they all came out as one clump is called the grand unified theory. And then there's a term or expression called symmetry breaking that defines the order in which they basically broke apart or separated. Now, I don't know about you, but I'm getting kind of bored. This is too much information, even for me. So I'm going to move on right now to what gravity really is. Now, you may know what gravity is at a high level, but we're going to dive in just a little bit deeper into gravity, so you get it a whole lot better. So to start off with, let me talk about what the textbook definition of gravity is. It's the invisible force by which a planet or body draws an object toward its center. So when you jump up into the air and you come back down, that's gravity bringing you down. If you throw a ball up in the air and it comes down, gravity. You get the idea. Now, another principle of gravity is the stronger or the heavier an object is, basically, it has a greater mass, the greater the gravity will be. So if you look at our solar system, if you look at the planets in our solar system and you go, okay, which one of them has the most and least amount of gravity? Jupiter has the most because it has the largest mass, and Mars and Mercury have the least amount of gravity due to the fact that they have the least amount of mass. So essentially, I sometimes I think about, well, what actually would happen if we had no gravity? And here's what I've come to the conclusion. Here you go. Okay. I'm going to count down, and when I get down to 0, let me show you what's going to happen if we lose gravity in 3 seconds. 1, 3, 2, 1, 0. Basically, what's going to happen is I'm going to be floating into space, and you will be too, assuming you're not bolted down to the earth. The oceans will start floating. The atmosphere will start floating into space. The core of our Earth will start doing bad things, and basically the Earth would be no more. So if you think about it, we take it for granted what gravity is doing for us, along with the other fundamental forces. But you need to be thankful, because without it, we'd be in a heap of trouble for sure. So there you have it in terms of what gravity is. Now you're an expert in it. Now we can move on to what causes gravity. And this is a real simple one. It shouldn't be really that difficult to understand. It's the curvature of space-time that causes it. Of course. I mean, come on. What's the big deal? Now, for those that have seen a few of the prior episodes, or one of the prior episodes, it doesn't really matter how many, I swear I keep on talking about space-time in every single one of these episodes, and you're probably getting tired of me talking about it, but it just goes to show you the importance of space-time. It's central to the function of the universe, and it'll become even more evident again as we go down the road here in terms of the other episodes. And for those that have no idea what space-time is, it is a term that was coined by Einstein as a part of his theory of relativity, where he decided one day, I'm going to join space, which is three-dimensional, with time, which is one-dimensional. And I'm going to create this 4D model of our space around us. And I want to do this because I really want to confuse people. And he's done a great job at confusing people because it's a really hard concept to understand. But anyway, you go, okay, I sort of get that now. Now, how does space-time curve? I don't even know what that is. So let's use our good old Earth to describe that. So here we have our Earth rotating at 1,000 miles an hour, orbiting the sun at 67,000 miles an hour. And if you weigh the Earth, its mass is 13 septillion pounds. Now that's a big boy there for sure. Now, in the whole scheme of things, is the Earth anything special beyond any other planet in terms of on the average throughout the universe? No, not really. But the fact of the matter is, it's big nonetheless. Nonetheless. So you think about this thing Earth, just hurling through space with this spinning and orbiting and just traveling at this speed with this mass, and you go, it's hard to believe that motion is not having an impact on space-time. And if you did think that, you would be correct, because it is. Now, here are some words to describe the impact that the Earth traveling, and any other object for that matter going through space-time, what impact it's having on space-time. Words such as sagging comes up. There is dimples form. There is curvature. There is warping. There's gravity wells. So all of those terms are basically referring to the same thing. You can think of that, when you hear those terms, you can think of, if you take a bowling ball and you throw it onto a rubber sheet, that rubber sheet's going to give. And that bowling ball is going to do its thing, it's going to do the orbit for a while before it settles. That sagging you can think of as gravity, the bowling ball being Earth. The heavier the bowling ball, the larger the sag's going to be, the larger the curvature. So you sort of hopefully get that analogy. Another one being, and this one's a little bit better from a standpoint of being more three-dimensional, because you think of a rubber sheet that's sort of just hitting just one part of the bowling ball. If you think of a ball, you put it underwater, and you're rotating it as you're moving it through water, you can tell that with that one, you can see that the water is basically space-time, because it's hitting all surfaces of the ball, and it's being displaced. And that displacement you can think of is the dimpling or the curvature or whatever term you want to use. So that curvature that we experience, or what is experienced when Earth is passing through space-time, is what we experience as gravity. That's what it is, plain and simple. Object moving through space-time, it's impacting space-time. It's basically space-time is being sort of pushed away, and as it's pushed away, it's sort of drawing from the Earth, and that's what we feel is gravity. So there you have it. You know what gravity is, and you know what's causing gravity. Now, the one thing you probably don't know is gravity has a special feature. It's really gifted. And what it does, or what it has the ability to do, is it can slow down time, if you can believe it or not. You go, okay, I sort of get gravity. I jump up and I'm drawn back down because the Earth is passing through the space-time. But how is it slowing down time? That one I don't get. Now, to answer that, let's go back to Albert's theory of relativity again, that space and time are as one. So essentially, as it's Earth is going through space-time, in addition to doing the suck or the dimples and all those good things, it's also basically sucking time too. Essentially, the more gravity that there is with an object, the slower that time passes. Boy, it's a weird thing, huh? It's one of my top 3 in terms of weirdness of the universe. And I don't know about you, but I get it, but I don't get it, and then I get it and I don't get it. But anyway, let me give you an example of this time situation. So as I sit here right now on my rear end on the ground, my rear end is aging slower than the top of my head because I'm closer to the earth with my rear end than my head. So I don't know what good that's going to do me. Maybe my rear end is younger looking than my head, but that's not going to get me very far, is it? I mean, whatever. But it just proves the point that, you know, it even though it's a small amount, it's actually happening. This is not just some theory. It actually is the case. Another example is, you know, if you're thinking about plastic surgery, you may want to put your face, if you want to look younger facially, you may want to put your face next to the ground more, because you'll age a little bit slower if your face is near it. Or you may want to walk on your hands and go about your life that way. You might look odd, but God, you're going to look good. You're ageless. You're going to look fantastic. All right. So now we have sort of an understanding of gravity, how it impacts things, in particular time. Now, universe just can't leave well enough alone. Not only does gravity slow down time, guess what else slows down time? There's one other thing that we're aware of anyhow. Who knows? Maybe there's dozens out there. But right now, time is impacted by speed. That's right, speed. So let me give you an example. It's documented, it's a fact. If you go 50% of the speed of light, time will slow down by 15%. That'd be 15%. If you go 90% the speed of light, time slows down to 50%. And if you go 100% the speed of light, time basically stops. So the higher the speed, time slows down even more. The higher the gravity, time slows down even more. So you see that inverse relationship between the two. Whether it's gravity or speed, the term that's used for this is time dilation. You're basically dilating the time based on either gravity or speed. And a great example of this time dilation for both gravity and speed are the GPS satellites that are circling the Earth right now. There's 24 of them, and they're positioned, so basically 24 because there's 24 hours a day, and they're basically orbiting the Earth. What's unique about the GPS satellites, and for that matter, anything in space, but I'm using GPS for the situation, that what's happening is, because that satellites are moving really fast, and I mean they basically orbit the Earth a couple times a day, they're moving at a good clip. Because of that speed, they're slowing down time. All right? Now, at the same time though, because they're further away from the Earth, gravity is not so great. So speed is speeding up for them. So you have this combination of it's slowing down because of my speed, but it's increasing because I'm further away from gravity. And at the end of the day, on average, a GPS satellite, it basically runs faster 38 seconds per day. So these have to be adjusted every day, whether, I'm not sure the frequency at which they do it, but if they did not do it, you may find yourself driving off a cliff one day because the GPS, they're not correct at all, both from a location and a time standpoint. So there you have it. We got ourselves gravity, and we know what causes it and what it is, and the fact is that time is impacting it, and so is speed. So it's a weird universe we live in, but that's the reality of it. And in episode 6, I'm going to get into electromagnetism, and that in of itself is another weird member of the Gang of Four. So have a good one, and I'll talk to you in episode 6. Bye.